到今天的 Functional Thursday。那这次啊，就是有请到 Matthias 来跟我们讲关于，我之前都把这个东西称作 Post-Quantum Cryptography， 但是现在好像有不一样的称呼了。然后我想要请陈汉来介绍 Matthias。
大家好，就是我们是在去年底的时候开始，就是成立这个 QSMC 这个量子迁移中心，然后接下来在马蒂亚斯加入之后又成立了一个就是密码学的实验室，然后就是我也从，我本来是一开始是之前是跟穆老师做研究，然后后来在这边当一般的那个 system engineer， 然后后来因为这个研究室成立之后，就是也转过来做跟这个相关的研究这样。那马蒂亚斯现在就是主要是在这个研究室担任这个研究室的主任这样。那他之前是在中研院跟杨国英老师有大概做个2-3年的研究，然后他是从德国来，然后据他说他是觉得台湾住起来比欧洲舒服这样，就一直延长他的那个居住的期间这样。那剩下我就直接丢给马蒂亚斯自己自我介绍这样。
Thank you very much for the introduction and thanks for having me today. I did not understand the words, so I trust it was all positive.
You will understand it after March, after you take
after I'm taking my class, yeah. I'll take a class in March. We may want to remove the plant and they can also see the slides. I just noticed, sorry. The big plant on the table.
Okay.
So, I'm here today to share a little bit about post-quantum cryptography, the research that we here at the Shor QSMC are working on, that I have been working on before at Academia Sinica and in my PhD. So my name is Matthias. I am the research director here. I have a PhD on applied post-quantum cryptography from Radboud University in the Netherlands, and my PhD advisors were Peter Schwabe and Brienne Young. I have about 20 papers on the stuff I'm talking about today, and you can download them all from my website if you want to. I'm a co-submitter of 3 cryptographic schemes for standardization called UV, Mayo, and Rainbow, some of which I'll talk about later. And I'm the co-editor of the ICR ePrint archive where all the cryptography papers are usually submitted. Before joining QSMC, I was a postdoc at Sinica, and before that I was a PhD student in Germany and in the Netherlands. And even before that, I did my master's also in Germany. We are some more people at QSMC doing research, so Hani, you all know. Maybe you also know Nick, who's also working with us on research. So what do I think you may be able to take from this talk? Because I think this is quite off topic for this Functional Thursday. So I have some motivations. I want to give a general overview of the state of post-quantum. We all have an idea of what this is all about, even though you may not be able to grasp all the details. You should have a rough understanding where we're at in 2024 for post-quantum crypto. Maybe you will see some relation to functional programming. Maybe in the formal verification part that might be related to what you're doing. And I want you to have some glimpse at what we're doing here. Ideally, I hope that I can get some of you excited about post-quantum cryptography, either in terms of research or just using the technology. Hopefully, we can get more people in Taiwan to study this, because I think there's still not enough people here doing research on it. And we, of course, also hope to attract people to QSMC in the future, either for research or engineering. So you see I have way too many slides. I don't need to go through all of them, so if you do have any questions, please interrupt me and we can discuss. I guess that's much more interesting than me talking for 90 minutes or so. So please interrupt me if you have any questions. Okay, post-quantum cryptography. What we call post-quantum cryptography is basically public key cryptography. But in addition to that, it's supposed to be resistant to attacks by both classical and quantum computers. But what's the important part, and that's often missed if I talk to people that don't know anything about it, for example my parents, then is that they need to run on classical computers. So we need to be able to use them now. so that we can protect the data now against attacks in the future. So it needs to be resistant to attacks from a classical quantum computer, but it needs to run on classical computers. So we have to use it much before we have quantum computers that are large enough to do anything useful. And this all goes back to, the main motivation goes back to the 90s, a paper by Peter Shor, where he showed that if you have a large enough quantum computer, you can do things that you can't do on a classical computer. You can do polynomial time, prime factorization, and solving of discrete logarithms. This paper was big breakthrough in quantum computing, but unfortunately it also solves the two main problems that we are basing public key cryptography on. Which means that all the public key cryptography we have, all elliptic-curve cryptography, all RSA, all Diffie-Hellman, all this stuff is no longer secure when we have a quantum computer. And yeah, in the 90s, a few people cared about it, but not many. In the early 2000s, this became a research topic. And many researchers around the world have looked at, actually not so many back then, but a few started looking into this, thinking of how can we do cryptography, public key cryptography, when we have quantum computers. But yeah, so back then there was a small conference started called Post-Quantum Cryptography, Crypto, of a couple of dozen people attending there, including Guoyin Yang in Taiwan, that he was one of the very early people to look into this. But then, not so much interest from people outside of academia was there. This changed in 2015, when the US NSA announced they want to move to post-quantum cryptography. And then shortly after, triggered by this, the US National Institute of Standards and Technology, NIST, said they want to replace their standards for digital signatures and key establishment with post-quantum alternatives. So they put out a call asking researchers to submit proposals of how these post-quantum schemes should look like, and then they run a project where they evaluate these submissions, and then in the end pick a standard, write it down in a standard document, and then make it binding for everyone who wants to work with the US government. This happened like this in the past, for example, for AES or SHA-3. They also ran these kind of competitions, and we know usually it's convenient that everyone uses the same cryptography, so everyone is now using AES. It's fast, everyone is using it, we trust that it's secure, and that's kind of what we're hoping for here as well. They publish a standard, everyone follows it. So in 2017, there was the deadline for this, and then they cut it down in multiple rounds to less candidates, and now, 2022, they actually announced the end of this project and the selected schemes that they're going to standardize. So now we do have not quite standards yet, but we do have the schemes that we want to standardize, and they've now put out draft standards. So there's currently 3 draft standards that they put out. One is called Kyber. They're going to rename it to ML-Chem because Kyber, some companies have trademarks on this, so they don't want to use the name, so they'll rename it to ML-Chem, Module Lattice Key Encapsulation Algorithm. The other 2 are called ML-DSA, lithium, and the third one's called SLH-DSA, Sphinx Plus. So these are the schemes that we will have standardized very soon. The feedback period was until November last year, so now they're updating the drafts, and then we're expecting around mid this year that we will have standards, right? The end of Q2 or something like this is the expectation. And then I think it will happen very quickly that many companies, many software libraries, many operating systems will start supporting this. We'll be using it very soon. Maybe if you are a little bit familiar with elliptic-curve cryptography or so, that you might know what sizes we're used to right now. So if we think of Diffie-Hellman key exchange, if you do this with elliptic curves, then the messages you're sending are usually 32 bytes large. If you do signatures, then your signatures are usually like 64 bytes, so it's all very small, and we're kind of spoiled with that. If we look at the sizes that we'll have in post-quantum cryptography, look at Kyber, for example, the key encapsulation mechanism, you'll end up with public keys of a kilobyte and ciphertext of about a kilobyte as well. So we'll have to get used to sending much more data for connecting to a TLS server, for example. The signatures, this looks even worse. So the lithium will have around 2 kilobyte public keys and 3 kilobyte signatures. And there's other alternatives as well. But this is kind of the numbers that you kind of have to get used to now. And in many cases, this is maybe fine. I mean, if I connect with my laptop to a web server, I may not care if I have to transmit an extra kilobyte because I'm downloading a 4 gigabyte video anyway. But if I have some very small devices that send very little data and then they have to send an extra kilobyte, this might be a big problem. Yeah, so I think we will see these schemes in a lot of places during this year. But the research and the standardization of this is ongoing, so there's more things happening. So NIST is continuing to standardize schemes they're continuing to study schemes that they have not yet selected for standardization, and they think they're still interesting to look at, and if we look at them for another few years, maybe we standardize them later as an alternative. So there are currently 4 schemes in there. They're called BIKE, Classic Michelise, HTC, and Psych. Although since then, the last one got broken, so this is now completely insecure. Basically, there's the other 3 left. Continuing to study them, and we're expecting that they will standardize one of them at some point. Then they also decided to put out another call for more additional signatures. They say we want to have some other signature schemes. They're particularly looking for signature schemes that have smaller signatures and fast verification. And so if you remember from the previous slide, we do have like lattice-based schemes where you have like 2 kilobyte public keys, 3 kilobyte signatures, and we have these hash-based schemes where you have a very small public key but a very large signature. And now they're specifically asking for something that has a small signature and maybe a large public key. And the deadline for that was last year. They received 50 submissions, and they decided to accept 40 of them as candidates. So that's the stage where we're in. It's now a round of evaluation, and then probably there will be more rounds later, and eventually we'll have standards there. Okay, so this is the one slide overview of where we are at right now. So we do have these initial standards. There's drafts out. They will be final later this year. They do continue to study other schemes that will be standardized in the future. Then there's this other competition that I just mentioned, for additional signatures. And there are 40 candidates right now, and 2 of those are actually I'm involved in. So we've submitted 2 schemes, UOB and Mayo. I'll talk more about them later. Then what we also see happening now is that these cryptographic primitives are being put into protocols. So all the standardization organizations that do standardize any kind of protocols, they're now establishing or have long established working groups that update these protocols to support post-quantum cryptography. In some cases it's relatively easy, in some cases you have to redesign the protocol. Again, I only talked about NIST so far, but there's actually more standardizing organizations that are looking into post-quantum cryptography. So for example, ISO is also going to put out their own standards, and it currently looks like they're going to standardize Classic Michelise and Shor, 2 schemes that are currently not standardized by NIST. And I don't know how slow ISO is, but at some point we will have standards there too. And what I also see is that some software is also using other post-quantum cryptography that is not standardized by either of them. So for example, if you're using OpenSSH, then you see that they have integrated and enabled by default entry prime, which is a scheme that's not under consideration by NIST or ISO. And there's some other software also using some non-standard. What we also see more now is governments actively pushing this. So the US has issued a memorandum to all of their agencies that they need to migrate to post-quantum cryptography. In Germany, we have a similar. So it's called BSI, their federal agency for information security, and they also published guidelines on we need to migrate to post-quantum cryptography now. And this is happening in other countries as well, that there's now guidance from the government that we need to do this migration, how we need to do this migration. And I think that's also going to get more. And what we also see, and that's I think is, for me this is very nice, is industry deploying this now. So if you're using an Apple device, they have announced yesterday that they're gonna migrate iMessage to post-quantum cryptography. I don't know when they'll roll this out, but very soon, if you use iMessage, you will use Kyber to encrypt your messages. And Signal has done something similar that's already protected by Kyber, and all the other software will follow. And that for me is very exciting. You've been working on something like this for many years, and then suddenly you actually run it without even doing anything, and it's pretty nice. Okay, so this was kind of sort of the very high-level introduction of what post-quantum cryptography is. Are there any questions so far, or otherwise I'll dive into more what we're actually doing. All clear? Okay, good. So we have 3 research areas roughly. I'll not talk about all of them today. One is new primitives, so that's more in the direction of future schemes that we develop to standardize later and then use in a couple of years. Another area is formally verified post-quantum software, and that's what I will mostly talk about today. So, software implementations of post-quantum cryptography and how we make them fast and how we make them secure. Third one is post-quantum hardware. That's also a very important topic. So we need, because these post-quantum schemes are very different from what we're using today. We need different hardware, we need different accelerators, we need different chips to do this stuff. So there's a lot of open problems still there. I'll not talk about this today. Okay, so this is roughly my agenda. I'll first talk about fast post-quantum software implementations, mostly on ARM, 64-bit ARM platforms. Then we will go into how we can formally verify the correctness of these implementations and how we can protect against side channel attacks. And Han will help me here and give a little bit of an overview of one of the projects we're doing. And then, if I still have time, I'll talk more about the future schemes. If I run out of time here, that's okay, and I'll go through this very quickly then. That's fine. I think this is a lot already. Okay, post-quantum software. So I kind of have to do the impossible now to get you from not knowing Kyber to knowing what are the actual problems we're facing that we can publish papers about. So I'll kind of have to do that very quickly. If you do fall asleep, that's okay. Then you just have to you can go to sleep now, and I'll tell you at which point you should wake up again when the interesting stuff starts. Then you won't be able to understand much, but if you believe all I'm saying, then maybe you can still see what problem we're trying to solve. Okay, Kyber, or as it's going to be named in the standard MLCAP, is the standard for post-quantum key exchange. So it's the only one that NIST has picked. So that's what you're going to use in many, many places. This is based on what's called the module learning with errors problem. So that's a mathematical problem. If you can break this problem, you can break the purpose system. Or in other words, we say if you can break Kyber, you can break this problem. So there's kind of a reduction between two. This is related to the other scheme called the lithium. So they're based on very similar mathematical problems and polynomial rings. So they got submitted together by almost the same set of authors. So they have, if you look at the two specifications, you'll see a lot of similarities. This was first published in a paper in 2017. But there has been many works before that are very similar. So you will see many similarities to a scheme called New Hope from 2015. But even before that, there have been other schemes that are very close to this. But in recent years, more people have been looking at how do we actually instantiate this to get something that's fast in software and hardware. How do we instantiate this so that we can actually implement it without timing side channels? This has been becoming more of a priority. This one is actually designed to have fast polynomial multiplication using the number theoretic transform. But it's basically baked into the scheme that the ring, the polynomials you're working on are chosen in a way that you can do very fast polynomial arithmetic. That's been baked into the specification. So basically, the specification tells you how you do your polynomial multiplication. And if you're implementing this, you will need to know that there's two operations that are dominating all of the runtime. One is polynomial multiplication using the number theoretic transform, but actually you will see that there's one thing that's even more expensive than that, and that is hashing and pseudo-random number generating using ketchup, SHA-3. So that's used in many places in the scheme for generating of a matrix A and in the FO transform. Yeah, I didn't talk about what that is, but that's okay. So a lot of hashing is going on in there, and if you want a fast Kyber, what will really help you is having a fast hashing. So if you have a hash accelerator or you have dedicated instructions on your CPU that do catch-up, then this is going to help you a lot in achieving good performance for Kyber. And this, I think, is the slide with the most math. I'll go through it very quickly. So this is the basic idea of all LWE-based schemes. And I assume you've somewhat seen how the Hellman looks like. So that's kind of what we want to build, but we can't quite build the different lattices, but it's going to be very similar. So what we're going to do is there's two parties, Alice and Bob, and they want to agree on a key that they can then use to use some symmetric cipher to encrypt a lot of data. And we're going to work with polynomials, so all of the letters here are going to be polynomials. And what Alice and Bob do is they pick two polynomials, we call them S and E, from some distribution. We'll talk later about what this distribution is, but you can for now think of these are polynomials with small coefficients. And the entire polynomial will be, the polynomial coefficients will be modular prime and cube. Polynomial, small coefficients, 1 cube. And then both sides will compute A times S plus E, where this A is some shared polynomial. So they agreed on this upfront. They'll compute this, and then that gives them what you can call their public key. And then they exchange this, these public keys. And then it's supposed to be hard to recover this S and E given just the B and the A. And so the idea is basically if you would have this without the E, without this, it's called the error, it's easy to solve. You can simply just invert it. But if you add a little error, then this becomes hard. It's what's called the learning with errors problem. If you then get this public key, then Alice and Bob can multiply this by their own secret. So Alice computes U times S, and Bob computes B times S prime. And what they will then get is A times S prime plus E prime is S. And Bob gets the same in the first place, but on the right it gets a little bit different. So they get different values, but since these S and E's were all very small, this error term here is also going to be very small. So you can have some So these will be approximately the same, and if you then apply some rounding, you can make them the same. In this way, Alice and Bob can agree on the same value. So that's kind of the basic idea of many lattice-based chems, and then there's a lot of details that I will not talk about today. But that's kind of how this is working. So what you need to implement this is polynomial multiplication here, and then there's a lot of stuff around it that includes a lot of caching.
So P and P are exchanged information.
Yes.
And what about
Yeah, so that's in the earlier schemes, this was something that was just a system parameter. But that's something we don't like, because then you don't know where is this coming from. Did the NSA create this A, or where is it coming from? So modern schemes let one of the two parties generate this A, and you don't need to, because this is a public value, you don't need to store the entire A. You can simply store a small seed, and then you use the pseudo-random number generator to expand this A from the seed. So in the end, this will be a seed that's part of the public key values.
So I presume that A is something both parties have.
Yes, but we don't want to write this into a standard, because then how do we choose it? So that's why we want this to be part of key generation. So Alice generates this A, or Bob generates this A. Okay, what in this picture, what it looks like both parties are kind of doing the same thing, but in practice, what we want is, we will not build something like this, because with this we can't get the security we need. What we will build is a key encapsulation mechanism. So there will be one party that generates a public key, and then another party that can use this public key to encapsulate a key and send that over. And then so there's a separation of the two entities. But I'm kind of sweeping under that all under the rug here, so we can talk about the implementation part. So if you look at Kyber, you will actually see that this looks a little bit different. So instead of polynomials, what they're using is matrices of polynomials. So you will, if you look in the stack, you will see this looks slightly different, but the idea is the same. You will have entity-based multiplication. You will just have to do a few more of them. Reason for doing that is mostly practical issues, and that is that if you want to have a scheme where you have multiple security levels, so you want to have a security level that's relatively small, but maybe you're not so confident it's still going to be secure in 30 years, and you want to have a higher security level that's very conservative. Then in the previous slide, you would use larger polynomials. But then that means you need code that supports multiple polynomial sizes, and that's very annoying to do in high speed. And that usually means you write your polynomial code for each size, and that's annoying. But in this case here, you can simply change the size of your matrices. So the code of your polynomial arithmetic will not change. That's one of the benefits of doing this. What in Kyber you also need is what's called the Fujisaki Okamoto transform. This is used to use what's called CCA security, and I'll not talk about this more now. And what they use for this noise distribution that was in the slides before is a centered binomial distribution. It's relatively simple to sample from a centered binomial distribution. That's why they make this jersey. So how familiar are you with Fourier transforms, FFTs? Okay, then that's gonna be tough. Okay, so entities, number theoretic transforms are kind of FFTs, but in a finite field. The general idea is we want to multiply two polynomials, and we do that by evaluating these polynomials at points, and then we can work on the evaluated values, and then later we interpolate back the polynomial. And then, of course, working on these points is linear. So you do these transformations, then you do linear multiplication, and then the inverse transformation. And by doing this transformation, so this evaluation in a very clever way, you can do this in n log n time. And that means the complexity of your entire polynomial multiplication is n log n, which is much better than n squared, which you would have for school multiplication. And yeah, so similar as for FFTs, this works because there's what's called fast Fourier transform algorithms or fast algorithms that compute this number theoretic transform. And if you've ever written an FFT, what you will see there is that you usually implement what's called a butterfly operation. And these look the following way. So you will have in this butterfly operation two coefficients of the polynomial will go in. You will multiply one of these coefficients by a constant that's usually called the twiddle factor. And then you take this and subtract and add it to the other coefficient. If you plot this as a diagram, then it looks like this. Two coefficients go in, the second gets multiplied, and then you add and subtract, and you get the two coefficients out. And this, in some angle, looks like a butterfly. That's why we call this a butterfly operation. And we scale this to larger polynomials. Then we just do multiple layers of these butterfly operations. And if you work out the math, you will see that this is actually computing the evaluation of this polynomial at the roots of unity, at the nth roots of unity, giving you endpoints that you can then work with on the point points. So yeah, for the larger polynomials that we're using here, we're using polynomials with 256 coefficients, so you need to scale this a little bit larger, and then you do 8 layers of entities, and that's how you implement this entity operation. So to put this into code, because that's what we want to do today, we need one more thing. And that is, how do we do this multiplication with this constant? And what's often used for this is what's called the Montgomery reduction. And you've probably also never heard of Montgomery reduction, so I'll need to introduce that as well. So what we want to do is multiply values. And if you multiply to n bit values, you will get a 2n bit value. So you kind of need to reduce the size again, otherwise your numbers grow too big. And Montgomery reduction is one way to do this. So for this, we will assume that q modulus is going to be an odd number. In this case, it's usually going to be a prime. For it to work, it only needs to be odd. And r is going to be a power of 4. The r is actually usually going to be so that it fits in one word. So if you have a 32-bit platform, r is often going to be 2 to the 32. Or if you have a different size, it might be 2 to the 16 or something like this. So one observation that you will have is if a is a multiple of r, this actually is quite easy. We can simply divide by r by shifting. So this is very cheap. So if a would be a multiple of r, there's no problem. So the idea of a Montgomery reduction is we will add multiples of q until the number we have is divisible by r, and then we can simply shift, and that way we have a much smaller number. And that's what a Montgomery reduction is actually computing. So it takes this number a and adds a multiple of q, where this multiple is computed as the inverse of q times a mod r. So this computation is not mod r, not q. In this way, if you add it here, this will, so if you take this mod q, it will be the same as a, because it's a multiple of q. And if you take it mod r, it will be 0. So the number will be divisible by r. That's the two things we want. Yeah, and actually this you can compute relatively cheap because the multiplications are now more hard. You just need to keep in mind that your result is actually not the same 1/q, but it's multiplied by the inverse of r. And actually that's not a problem because we can simply recover this real value later, and you only have to do this once in the very end. That's kind of how the idea of that is. We can turn this into something that's called Montgomery multiplication. So here, not looking at reduction, but a larger multiplication. So consider you want to multiply A and B, mod Q, and we can, for now, assume that they have been converted to what's called the Montgomery domain. So they have been multiplied by R mod Q. So we have AR and BR. If we now do a multiplication of these two, followed by Montgomery reduction, what you will see is that first you have these two R's in there, because you multiply AR against BR, but then if you do the Montgomery reduction, one of these gets divided out by the inverse of R, and so the result will be A times B times R. This is the product in Montgomery domain. So that's how Montgomery multiplication is usually done. You convert all your inputs to Montgomery domain, then you perform as many multiplications as you want in this domain, and then in the end you can convert back to normal domain. So you will see this in many big num libraries. You will see Montgomery multiplication. But actually here we can do better because we need to multiply by a constant. What we can do is we have this constant already lying around in Montgomery domain, and then if one of the arguments is the Montgomery domain, and then we do a multiplication followed by a Montgomery reduction, the result will be in normal domain. So that's how XGTs basically work. Okay, now I need to move more to the actual hardware you want to look at. Or looking, for example, smartphone CPUs or what's in this laptop. So 64-bit ARM CPUs. And what you have on those is called Neon. So you have vector instructions that you can use to do many operations in parallel. We now want to somehow get this Montgomery multiplication in vectorized instructions. And what you can use for that is actually called the sign Montgomery reduction. And that's basically, the idea is that since we want to compute A times B minus TQ divided by R, in the sign Montgomery reduction, we can also just compute the two upper products separately and then subtract just these two. And that helps us to express this Montgomery multiplication in terms of low multiplications and high multiplications. Computing the lower half and the upper half. And this is how the full expression looks like. So the left side is just the high multiplication of A times B, and the right side is the low multiplication of A times B times this Q prime, which was the Q inverse, and then the high multiplication of Q prime. And why are we doing this? So we're doing this because one of this, so this B was a constant, so we can actually pre-compute more here, and instead of doing 3 multiplications here, we can pre-compute one of them. And that leaves us with this expression, which only has 3 half multiplications. And that's what's used in for example, AVX2 implementations of this. It's going to be using exactly in this way. But looking into the ARM platform, if you look up what instructions you have there, you will see that you have a vectorized multiplication. This is basically a lower multiplication, and you have a vector multiplication with addition and subtraction, but also lower multiplication. There is no high multiplication that will give you the higher half of your product. But there is other instructions. One is this one called SQD mul H. So this is basically a high multiplication, but it's doubling the result. And I think this is probably useful for some signal processing where you need this oftentimes. So it's doubling the result, but we can kind of work around this. So for example, in this way, there's a Montgomery multiplication of A times B, where B is a constant, so we can pre-compute some stuff. So you will do the high multiplication of A times B, you'll do the low multiplications of A times B prime, that's the pre-computed constant, and then you can take that, do a high multiplication with Q, and then you subtract the two. And luckily there is a subtraction that does halving the result, so this way you can undo the doubling that happened before. So this gives you a Montgomery multiplication in 4 instructions. But actually we found in a paper 2 years ago that we can do better than this by something that's called varied multiplication. And yeah, maybe I'll skip the details here, but in the end we showed that you can do the same operation in 3 instructions, just doing it a little bit different. And by using a different instruction called the RD mul H, so rounding, doubling, multiply. So that's kind of what we use now in neon implementations of entities. We can plug this into the butterflies we saw before, so we do one multiplication and then an addition and a subtraction to on the right side of the butterfly. And if you now run this on a real CPU, just write assembly like this, you'll see this will perform very poorly. And yeah, so we'll look at this CPU, this is ARM Cortex A55. This is a pretty common CPU on smartphones. It's the energy saving core on the Cortex X1 big little SoC. So if you have a high-end smartphone from maybe 2 years ago, then it's likely going to have a Cortex X1. Yeah, and these SoCs are usually like some energy efficient cores and some high performance cores, and if you don't have much load on your phone, the high performance cores will be turned off, and if you then suddenly have a lot of load, they get turned on. So we're looking here at the energy efficient one, and what's usually the case here is that these energy efficient ones, they will be in order and yeah, less powerful than the high performance cores. And that means they're particularly bad. So since they're in order, they can't reorder instructions on the fly. So if your assembly is bad, then you will get pretty bad performance on these CPUs. That's why we'll look at it here. So if you then look into the manual, you'll see that the instructions we care about actually have a latency of 4 cycles, which means that if you issue such an instruction, only 4 cycles later you can use the result. So in the meantime, if you need the result, you have to wait for it. The throughput of this is 1, which means that every cycle, one of these instructions can be issued. But this is actually a dual issue CPU. So the CPU has 2 neon execution units. So in theory, you can do 2 neon instructions per cycle. But of these, you can only issue 1, because only one of the execution units can actually do multiplications. So if you look at the 5 instructions that we looked at before, you can, because the CPU is in order, we know that it has to work on these instructions in exactly the same order we give it to them. You can actually look at the code and figure out how long it's going to run. And we start with 2 multiplications. They have a latency of 4, throughput of 1, and they can only run on one of the execution units. So we know we can't dual issue these because it only runs on one execution unit. So we have to it takes 2 cycles to issue these 2 instructions. And then in the next instruction, we're actually using the result. So we have to wait, and for this result to be ready, and since it's a latency of 4, we have to wait for 3 additional cycles. Then we can do the next instruction. But again, we need the result in the next instruction, so we have to wait another 3 cycles. So that these 5 instructions take a total of 10 cycles. Or if you need a result immediately after, then it's 11 cycles. And you see that this is pretty bad utilization because you waited in between. One of your neon units was idle most of the time, so this was a lot of waste. So what the developer will now do, he will try to come up with ways to keep all of your neon execution units busy. One immediate thing is to do 2 of these at the same time. So you just duplicate all of this and work on 2 parallel data streams at the same time. And this way you can at least hide some of the latencies in between. You can work out the cycles later by yourself if you want, or you can believe me that this is now 12 cycles for doing 2 butterflies. This is better. So this was 10. This is now 12 for 2, so 6 for 1. This is much better already, but still very far from the optimal execution time of 3 cycles. And now, how do we go from here? So what we did for many years is then sit down and think, how can we do this better? But this gets very annoying. So we at some point decided we don't want to think anymore, so we'll write a tool that does the thinking for us. And that's what we call SLOTty. It's called super lazy optimization or tricky handwritten assembly, where we solve exactly this problem. So we have some assembly and we want to optimize it to have as few stalls as possible on our microarchitecture. And the way we approach this is by modeling all of this as constraints. So you model the data dependency between your instructions as constraints. You model all the latencies and throughputs as constraints. Ideally, the result should not be consumed within these latencies. You model the restrictions of the execution units as constraints, and often you have instructions that have forwarding paths that, like, you have a multiply accumulate that usually has this latency, but if another multiply accumulate follows, you have a forwarding path, and then it's faster. And you model all of this as a constraint, and then you feed this into a generic constraint solver. And what we used here is the Google or R constraint solver, but you could also throw this into any other constraint solver that would be okay. It should work. We didn't try it, but there's no reason why it wouldn't work. And then you try to find a solution that does not have any stalls. This may or may not exist, but if it doesn't exist, you can simply allow it to have one stall. Or that also doesn't work. You can binary search for the minimal number of stalls you will have in your instruction sequence. And this way you can find the optimal instruction order to implement this. And we actually were a little bit surprised that this works so well. So we can feed in approximately 150, depends a little bit on the complexity of the code, and sometimes even 180 instructions or so, and we get results pretty quickly. And if your model was 100% accurate, this will be optimal code. And yeah.
I put the results of SLOTty into what you call the processor to message out.
So the question is if the code will mess up in the sense that it will be wrong, or in the sense it will be not optimal.
Because I'm asking if it will be not optimal.
Yeah, it's not going to be optimal. Yeah, it's optimized for the microarchitecture. But what's actually interesting, so on these CPUs, as I said, you have multiple different CPUs on one SoC. One of them is some of them are in order, energy efficient, and some of them are out of order and high performance. So if you run software on this chip, suddenly in your execution this could switch to another core, so which would have a different microarchitecture. And then it's usually the case that if you optimize code for the in-order CPU, it will not be worse on the out-of-order because the out-of-order CPU can just reorder it anyway, and then this non-optimal ordering is less of an impact. So this tool mostly helps you for in-order CPUs, because there it's really important that your instructions are in exactly the order that you can issue them in multiple at once. But yeah, in theory, this is per microarchitecture you optimize. So the process for how we use this tool is you would write readable assembly, which you can use macros or whatever you'd like to use, but you don't pay much attention, any attention at all to the latencies. You just ignore that. Then you feed it into this tool, and it produces optimal assembly according to the model that you gave it. We actually got very, very good results for in-order CPUs, and we also managed to get relatively good results for simple out-of-order CPUs. For example, the ARM Cortex-A 7 that we find in the Raspberry Pi 4, there we also got pretty good results. If you try it for more complex CPUs, like the Apple M1 or something, that will have much more out-of-order execution, much more crazy stuff happening. There it's pretty hard to come up with a model, because the instruction order is harder to, it's harder to, because it's not so important that the exact order of the instructions is there. It's just important that the CPU always has instructions that it can issue, but it can execute them out of order, so it might look ahead of a couple of instructions. Yeah, so there we're still trying if we can get better results, but mostly for in-order CPUs this helps a lot. So for the examples we looked at, we can match or beat the performance of hand-optimized assembly. And what we find very nice is that this assembly that you feed in, it's much easier to read, so it's also much easier to audit. And what we often see also is that it results in much more compact code. And I think I need to speed up a little. What it can also do for you is register allocation and register renaming. So you can, sometimes you need to use different registers to be able to reorder your instructions. It does that for you. What it can also do is software pipelining, which is a very nice thing. So imagine you have a loop body that consists of 3 instructions, A, B, and C. But actually, in some cases, it might be faster to compute CAB or BCA, to do this in a different order. What you can do is rearrange your loop and just merge some of the instructions in the previous iteration or some of the instructions in the later iteration. This is called software pipelining. And if you have a loop body of a couple of dozen instructions, it's impossible to do that. But this tool can actually do this for you, and it's pretty good at finding fairly crazy code that gives you much better performance than what you feed into it. What you then, of course, want to do is to scale this up, feed in much, much larger examples, because if you feed in more than 150 instructions, this usually blows up the number of constraints, and then it doesn't terminate anymore. So we looked into how can we maybe make this still work for larger examples. We looked at an X519 implementation that has around 1,000 instructions. And what we found is, what we implemented is basically some heuristics that still allow you to optimize larger code pieces, but you will lose this optimality of the output code. But we still managed to get code that's beating the state of the art. The easiest way to think about this is, if your code is too large, you will split it into multiple overlapping pieces of code and optimize these individually. But then you of course have to repeat this a couple of times to be able to, instructions can move from one part into the other part, so you need to repeat this a couple of times. That's what we implemented here. Yeah, so the code that came out of this now is used in multiple libraries. So ARM has merged some of the complex FFTs that we looked at. AWS is now merging our X519 code, and some people have even tried integrating this into LLVM, so you can just make it part of your compilable chain. Okay. Any questions so far for this part? Of the constraint solving. Well, it is hard, yeah. I was surprised it works at all for these sizes. Yeah, it just doesn't scale, of course. It doesn't.
Okay, formally verified software, and I think this is, I will only cover the second part and I'll skip to the end, and then we can, okay, do we need to motivate formal verification of cryptographic software? Maybe we don't. I'll start with an example. So this is an implementation, or part of an implementation of the lithium that was in a reference package that they had submitted. I'll tell you what this is supposed to do, and then you will tell me where the bug is in this code. What this is supposed to do is to sample a polynomial. So this A is going to be a polynomial of n coefficients, and each of these coefficients is supposed to be 20 bits long. Random 20 bits. It does that by taking a buffer with random bytes, and then, since each coefficient should be 20 bits, it takes 2.5 of these bytes to construct one coefficient. Or in other words, it's taking 5 bytes and constructing 2 coefficients from that. That's what it's doing here. It's taking 2 from the buffer and then another half, and then it does this for the other coefficient, the remaining half, and then the other 2. And then yeah, it actually does some checks still if it's smaller than a certain threshold, because the threshold is a little bit smaller than 20 bits. And if that's the case, it will put it into the polynomial. If not, then it will throw it away. So if you run this, plug it into the lithium, it will work. Everything is fine. But can you see what's actually wrong here? So this T here, that's used here, it's just one variable. So it's basically overwritten here. This is completely irrelevant, and it's writing the same coefficient to both coefficients. Which in many pieces of software maybe it doesn't matter so much, but in this case it completely breaks the scheme. The security of the scheme, though, because this will result in 2 coefficients, 2 neighboring coefficients of the polynomial being the same, and that makes, in this case, means you lose all security of this cryptographic scheme. So this code works perfectly fine, but it's just wrong and insecure. And the fix is very easy. You just use 2 variables here, and then it's okay. So we kind of need to make sure our code is correct. And for crypto code, this is crucial. If our code is not really correct, then we often can just not do any crypto at all. So we want to have guarantees that our code is correct. And I think the past has shown that the ways we do that right now are not good enough. Most people now would yeah.
Tell me why that makes this.
That's needs more context on how the scheme is constructed. But in the construction in the lithium, this gets multiplied by the secret. So this coefficient, this polynomial will be multiplied by the secret. And then it will be part of the output. And you need more context to understand why it's this, but it was pretty bad. But you can't see that from the slide yet, you're right. And part was more, there's a bug, and it can have very bad consequences, so we need to catch these bugs. Then in crypto we have more. So even if your crypto is implemented correctly, you may still leak secret information through side channels.
So particular timing side channels we're looking at. So, for example, if you have a branch in your code, then this branch condition will leak. Because if the branch is taken or not, the different branches may take different times, or even if they take the same time, you have a branch prediction, then will leak if the branch was taken or not. So you should not branch on any sequence. Similar for memory accesses, most CPUs now have a cache. These memory accesses actually leak what kind of cache line was accessed. So if you access memory, then these memory addresses are leaked through timing side channels. And then there's a third class of timing side channels. These are data-dependent instructions, data-dependent timings of instructions. So some instructions have timing that depend on the data you're processing. So for example, division instructions, they're always depending on what's the input to the instructions. And then often these attacks have very, very bad consequences, and often they can even be exploited remotely. Countermeasures are relatively well understood, so we just do not branch on any secret conditions, we do not do any memory access at secret locations, and we do not use variable time instructions. So that was kind of the state of a couple of years ago. We thought, yeah, this is kind of solved now, we can just use what's called constant time code. But then, in recent years, more bad things have been coming out. So these are in the realm of microarchitectural attacks. And these are microarchitectural effects of the CPU that are also presenting side channels. There have been numerous. They somewhat tend to have fancy websites and logos. I'm not sure why that's the case, but you've probably heard of Meltdown, Spectre, and Hertzbleed. These are all very bad for crypto, and for some or many of them, we don't really know yet how to protect against them. Or it's so expensive to protect against them that the CPU vendors don't want to do it. One example we want to look at more here is Spectre variant 1. And this is a 3-line example of seeing how Spectre v1 can be a problem. So what we're doing here is we're looping through an array. So X is going to be the index, and we have a loop going over an array called array 1. That's size array 1 size. And then we access from array 1, and we take what comes out of that and use that to index into a second array. And then we increment this X and go through the loop. So assuming that this X and the array 1 values are all public, this code does not have any traditional side channels. But what your CPUs unfortunately do is what's called speculative execution. So your CPU will try to speculate what kind of code is going to be executed next, and then just execute it already. And if it speculated wrongly, it will just undo the stuff it did. So for this loop, what this means is that it's going to execute this loop for a while, and then each time it has to predict, will I go into this loop again, or will I exit this loop? And if this loop is long enough, it will at some point learn, I'll always stay in this loop. So at some point, this X is going to be too large, and that means it will speculate. It will do all of this, but actually the value of X is too large for this array 1, so it's going to be read out of bounds there. And then later notice, oh, I've done something wrong here. I shouldn't have taken this branch, so it's going to undo that. But since these are memory accesses, these accesses went through the cache. So, and this is change in the microarchitectural state that cannot be undone. So this will basically leak the value into microarchitectural state. And for array 1, this is not a problem because it's public. But since we read out of bounds now, it depends on what's going to be at the memory address after that. And if that's a secret value, this code leaks the secret value. And this is pretty bad. And many people are worried about how we're going to protect against this, but luckily this is possible to protect against. We'll see in some later slides how to do that. Okay, yeah, that's kind of what we want to achieve. We want stronger guarantees for the correctness of cryptographic code, and that's what we call high assurance cryptography. What we kind of want to do is we want to prove an implementation to be correct, so implementing a specification, and to be secure, so to fulfill some security properties like being constant time, having no vulnerabilities against vector attacks. And yeah, so what we are working on is a project called Formosa Crypto. So that all of this project is high assurance cryptography that's ready for deployment. It's actually started by some European researchers, and it consists of 3 main parts. One is the EasyCrypt proof system, one is the Jasmine programming language and compiler, and the third is the libj, which is a library that's then written in this language and contains crypto implementations that are formally verified. So we'll give you a short intro into how this works. So this is the very high level overview. So what you will be doing is you write your cryptography in Jasmine. So you'll have a program here, so the Jasmine, that's your crypto implementation. You can feed this into the Jasmine compiler, and this compiler will translate it to assembly. And what's nice about this compiler is that this is actually certified compilation, so it's proven to preserve the semantics of the Jasmine program. And part of this is due to the Jasmine language restricting you to things that are sensible in cryptographic code. But what the Jasmine compiler can also do is extract it into an EasyCrypt model that we can then use in the EasyCrypt prover to prove things about this program. What you, for example, can do, you can write your specification of your crypto system, also in EasyCrypt, and then you can prove interactively that your Jasmine program implements the specification. That's kind of the goal, what we want to achieve here. So prove that our Jasmine program is implementing the specification. And Han will give us some more information on this now.
So, okay, I will have a brief introduction for Jasmine programming language. It's basically with a C-like syntax, but for aligned in Jasmine, it's actually aligned in assembly. And if you don't bear this in mind, then you will have a lot of troubles when you're writing the program. And so programmers can control quite a lot of low-level details that are performance critical. Like you have to do register spelling by yourself, and you can call assembly instruction like AVX2 instruction, for example. And the programs itself can automatically provide some flags. Then you can check for like safety and termination. Then we'll see it later. So this is an example of Jasmine calling assembly instruction. So the left-hand side is Jasmine language. So you can see it's quite like a C. You have colon at the end, and there's something that they're inspired by Rust. So for example, this function, and what you have to, I can use. So Jasmine can compile the code to assembly. Then afterwards, you can link the assembly code into whatever language you would like to use, like C or Rust. And only the export function can be used in the other languages. So there are some instructions, like for example, the instruction I called is vector add for C. 16 8-bit unsigned integers. And so there are also there isn't a lot of detailed there isn't like perfect documentation for the language itself, so you have to take a look into the compiler. For example, this one. So the compiler itself is written in OCaml, and this is, I'm not sure, this is the parser of OCaml, the parser framework of OCaml. I'm not sure which one they used, and so these are the available instructions. And this is the example of termination checking. So as you can see, this will definitely not terminate. And by Jasmine, if you provide this check safety, it will you'll see that it cannot terminate. And the reason that you can do the check is cannot clear. So this paper has said that Jasmine is based on another proof of system called Daphne, and it is based on Hor logic. So I cannot. Maybe I can. This is. Here, so it's basically that if you provided the variable that which is strictly bounded, well defined, and the variable will get strictly decreased in every iteration, then you can prove that it will terminate. So this is how Jasmine did it. And for loop, there's two different kinds of loop.
To use that, as it showed just now,
we don't have to use Daphne. It's baked in the language. So yeah. So all I have to do is just provide a flag called check safety. Then you will check the termination for me.
So does it involve use Daphne internally?
So from the paper, it seems like it used Daphne internally, but from outside, I didn't look through the paper. Yeah. So there is two kinds of loop in Jasmine. One is for loop, and it actually just unroll all the instruction. So you can tell it from right hand side. And there's another kind of loop called while loop, and so you can see that for example the sum function, at first it's jumped to the sum 2, and then after, so here this compare is to check for the condition. If it's hold, then you will jump back to the sum 3, and then if it doesn't hold, then you will go to the last instruction. So this is while loop, but the while loop cannot pass the SCT check, which is the spectrum protection. So we have to do a little bit more things to make it safe, which is with some more instruction. And what the instruction do is we insert a thing called ellfence, which is indicator to the compiler that tells it to that whether the branch prediction pass or is it successfully speculated or misspeculated?
To CPU.
Yeah. To CPU. Yeah. So this is the ellfence where generated which comes from the init MSF instruction, and so we have to update the flag like in every iteration, and also after the iteration. And this, so for let me check. I think I would like to skip this. So for achieving generic, currently there isn't very nice way to, the language itself didn't provide any generic function. So what I can do is to, like, for example, I have to use in a file called sum.jinc, I have to provide I can have a function. It depends on the value len, and in the file I will not specify the value of len, and in another file called param.jinc I can have I can specify the value of len. Then in the main.js file, all I have to do is just to include the correct parent file, and which is the way we can do to like to implement the cryptographic implementation with different parameter sets.
Okay, thank you. Yeah, so adjustment allows us to write cryptographic code, and then the adjustment compiler already can support a bunch of checks, second check, the constant time check, and the speculative execution check. That's what Han showed here. But the important part is then afterwards we can extract it to EasyCrypt, and then in EasyCrypt do proofs about this code actually being cracked, and you can also prove about it non-leaking through time-side channels. So a lot of the stuff happening, and this has been done by other people. There's been a lot of people working on Kyber and other cryptography. There's some more work on the other standards, and a lot of things have been happening in just on EasyCrypt. So this is not our work. So what we're doing is basically using these tools, and we're currently working on a formally verified implementation of ProtoCam. We basically have a decimal implementation of that. Done the constant time and memory safety inspector protection stuff, and we're now working on proving this correct in EasyCrypt. There is some other stuff you can do. You can actually prove that the code is actually implementing specification. You can prove that there's no information leaked through timing, and you can even prove things about a cryptographic scheme. Like you can prove that ProtoCam actually is secure if LWD is secure. Okay, now I think I will skip this third part, which was about more post-quantum signatures. If you want to hear more about this, I will talk about this in some other place, I'm sure. I'll skip to the end, to the conclusion. Talk a little bit about what the future directions here are. So, talked about this tool called plotting. So we've published this at Chess, the crypto conference this year. So what we now basically want is more users to use this tool. So we have set up a website so you can find information there, and we'll also be doing some tutorials next time. Of course, we want this to support more cryptography. I think an obvious candidate is Ketchup because it's used in so many places. We want this to support more platforms. For example, the Apple CPUs are interesting, but Apple doesn't give us much documentation, but it makes it a lot harder. ARM is a lot more friendly. They give you nice documents where they write latencies and throughputs and general descriptions of the pipelines. What would also be nice is optimal still code generation. So if you don't have enough registers, then what would happen right now is that it just fails. But it would actually be nice to look at where do we need to spill in an optimal way. And maybe we want to automatically create these models because that's right now a lot of work to create these models. Fault verification, I think I've probably talked about what we're doing with Jasmine and EasyCrypt, but what I did not talk about is CryptoLine. Since some of you are from Academia Sinica, you've probably heard of CryptoLine before. This is a tool designed by researchers at Sinica. They have a slightly different approach from what we presented here. So what they get is, the input to this is straight line assembly, or usually they do it by executing a trace of the program in GDB, and then you translate this into CryptoLine language, into their own domain-specific language, and this is pretty close to assembly. So usually just consists of like regular expressions that you place it, and you provide your pre and your post conditions to your code. And then you can verify these with other tools. Algebra is verified with computer algebra systems, and range conditions are verified by SMT solvers. So this is a slightly different approach from Jasmine. And it works well for certain things where Jasmine is not very good at it. And that's why they are working on now on combining the two and using CryptoLine for the arithmetic parts where CryptoLine is very good, and using Jasmine for the other parts. But we are actually working more on the implementation side. So we are working on verifying one of our oil and vinegar, the UV, one of these crypto systems that I did not present. We're working on formally verifying one of those. In terms of the new signatures, I didn't tell any details, but this is, I think, we'll still be able to follow this. So there's currently an ongoing first round of evaluation. Started when NIST posted the candidates in July last year. There's going to be a workshop in April this year. And then my prediction is that they will announce the second round of evaluation at the end of this year. And then maybe cut down from the 40 schemes they have right now to maybe 10 schemes. And then maybe end of 2025 or sometime 2026 they will select their standards. What we do right now is also the formal verification efforts that I mentioned, and we're also running some larger scale experiments to see how it actually affects real world deployments if you use these signatures instead of the others we have. Yeah, that I would like to thank you very much for your attention, and we still have some more time for questions.
Is Jasmine project, is it a formal verification project by cryptographers or cryptographic project by formal verification people?
Yeah, so you kind of need both.
Yeah.
So if you look at the website of this Formosa crypto project, you will find like 50 names or so that are actively working on this. I'm not sure if these would be people that you would also know if you're more on the formal verification side, or if it's too many names for me to. But you kind of need both expertises, plus more. So what we want is that it's implementing the specification correctly.
Alright, so you didn't put the specification this part is compensated.
Okay, this is so for the implementation correctness, we want to prove that it's implementing the specification. That's one part that we mostly care about here, because that's what goes wrong in real life a lot. But what they of course also care about is that your scheme is actually secure. And that you do by security proofs. And these security proofs then show, okay, this crypto system is secure if your mathematical problem is hard. And that's something you can also do in EasyCrypt. So you can then prove the specification to be in CPA secure if LWE is hard. So that's a different part that you can also do in EasyCrypt, like making your security proof really verifiable. So that's what they also do. Does that make sense? You look puzzled.
Yeah, that's also because I wonder what is EasyCrypt anyway.
You wonder what EasyCrypt is?
Yeah.
So I will not be able to give you a satisfying answer on this. It's a proof system that
I think it's based on order logic, this implementation of order logic, and it's the syntax is more similar to Tom, and then you can do sort of presentation that there is some tactics you can use to that's all.
So, would you agree that it's like Coq, but it has some features that help you with cryptography? Or?
I think it has some features that help with cryptography, since because it is based on probabilistic order logic. So order logic is you have some precondition, then you have statement and postcondition, then you have to prove that after a certain statement that given precondition, the postcondition is satisfied, and the probabilistic logic is the reason they have to use it is because there's some sampling, the randomness in some cryptographic implementation. So yeah, that's why I think that's the reason.
It's just being built on top of exactly something else.
I think it is higher level, but I'm not sure if it's solely built on top of that level, because their syntax are different, so I'm not really sure. But they're from the paper they are like related.
I was kind of lost. So, is sole treatment or general purpose?
What is general purpose?
I mean, is this particular for cryptography, or you can?
No. So one of the examples we looked at was a complex FT, which was used in signal processing. So it's definitely not specific to cryptography. It's useful in cases where you care about the optimal performance of a relatively short piece of code. So if you have an inner loop that's executed very often, and you really care about the performance of the program, then this is going to help you on certain CPUs. So I talked about 64-bit ARMs, but actually on the 32-bit ARM microcontrollers, if they're a little bit more advanced, so more like Cortex M7, Cortex M55, Cortex M85, some really complex pipelines, there it can help you a lot. Other architectures, who knows?
Well, I'm also curious about this language Jasper. That so from what I read just now, so it's a very low level language, and so every line corresponds to one line assembly code. But however, then why not just do it separately? So this language must offer something more than the assembly language. So
wants to what more does it offer?
Well, it has certain features that you don't have in assembly, like loops, variables that you can do automatic register allocation with, things like this that make it easier to write code and read code. But I think the biggest part is that it allows you to actually reason about it and have more, to reason about something you kind of need to have an understanding what area in memory is what. And if you have assembly, then you will just have reads stack.
So these are the limitations you have to the language, which allows you to do reasoning.
Yeah, this is part of the language, yeah. Yeah. Here's the other.
I haven't written like single line of assembly before. I use JSON. What good about using JSON is that I don't have to care about which register I'm going to use because it's everywhere. There's like different kinds of variable like register variable and stack variable. And when using register variable, I don't have to care which register I'm going to use. All I have to care is that there's no more register to allocate and I have to steal something.
Yeah, so this is what will usually happen. You write your code and then at some point the compiler says, I don't have enough registers. And then you actually notice this is not C. I need to think where I spill now. So this is more like writing assembly, but it gives you some help with writing it.
And you don't have to calculate the scaling by yourself. Like when you do when you use array, you don't have to calculate it by yourself.
More like the intermediate language, like
Yeah, so it gives you the full control. You can get the optimal performance. You can do almost everything it's in assembly, but it helps you with certain things.
So, do you have any questions? So then I think probably time to wrap up. So another the people also like before people also love to stay and chat and do discussion. So let's thanks you.
Thanks everyone for coming. I hope you learned something. And